Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. Starting with the name of Allah subhanahu wa ta'ala, the most merciful and the beneficent. In the previous lectures, we have studied system modeling technique in frequency domain. For system modeling, you want to represent a system, and for the representation of a system, you you started representing system in frequency domain with the help of transfer function. Transfer function basically characterize or the dynamics of the system in S domain or frequency domain. Similarly, you start analyzing the system response or system by the technique named as Laplace transform. Laplace transform provide the mathematical tool to analyze that S domain transfer function. In this lecture, we will start modeling the system in time domain, and for that purpose, for the time domain modeling, at first you want to represent the system in time domain. As you have represented a system in frequency domain, and that representation was known as transfer function. Similarly, system can be represented in time domain as well. So there are various techniques to represent a system in time domain. These techniques are commonly known to us in some previous courses. You might have studied that techniques. So, starting with the time domain modeling, first we want to represent any physical system. Actually, in this system modeling or in mathematical modeling, you want to represent any physical systems in form of mathematical model. So, if we say that if I want to represent a system in time domain, then there are various ways. One of the most common ways to represent any physical system in time domain is differential equation. So differential equation is used to represent, and similarly there are various other ways. For example, you can represent a system by the help of impulse response in time domain as well. But here in this course, in feedback control system, we will study that we will represent our system with the help of differential equation. You have known, you know that how we can form a differential equation. You have done in previous lectures as well. We will discuss it we will review that thing as well in this lecture. So what we can say about the differential equation basically provides an accurate mathematical model of any physical system that completely determine the system dynamics. So now we can say that there are two clear approaches for analyzing and designing of a system, or we can say the modeling of a system. One was the classical or frequency domain approach, which you have studied previously, and from this lecture we will start discussing the modern or time domain approach. In this modern or time domain approach, before moving towards the example and forming differential equation and uh, uh, analyzing those systems, first we must go through a comparison between both approaches, that why we are moving towards this second approach, what are the major advantages, what are the major disadvantages in between both approaches. So if I say that what is the major advantage of the frequency domain or the classical domain approach, the major advantage is that it rapidly provides this stability related information. You can easily extract out that the system is stable, extract this information from the frequency domain representation or frequency domain approach, that system is stable or not. Similarly, it rapidly provides the transient response information as well. But at the same time, there is a disadvantage, there is a big disadvantage of that classical approach, which is that it is only limited to the time invariant system as well as only linear system. That this classical approach of frequency domain approach cannot analyze a system which is behaving non-linearly or non-linear system. Similarly, if system is time variant, then the classical approach cannot deal with that types of system. So Moving towards the time domain approach, time domain modeling can handle the system which are linear, non-linear, time variant, time invariant system. Similarly, you can deal the system which are basically MIMO system, multiple inputs and multiple outputs at a time. So with the help of these time domain approach, you can analyze some really complex system. So there are some basic advantage, and generally you can also say that these alternate model gives the control system to the designer or analyzer another perspective, or you can say the different perspective from which that he or she can design any system, or he or she can view the different parameters of the system. So these are the basic difference. Now, as you have studied in the previous lectures, in the frequency domain approach, that we can model different types of system in frequency domain as well as in time domain. So these are the same systems which you studied in frequency domain. We will inshallah study the time domain approach on the similar systems. I will just have a quick review of those types of system. Firstly, you have a mechanical translational system which you studied in the frequency domain as well. What do you mean by the term translational? Translational basically basically represent that the system movement or the motion of the system will be on the straight line, or the translational mechanical systems move along a straight line, or the trajectory of that or the path of the movement will be the straight line. And the major elements where you can see in these mechanical translational system was mass, spring, and damper or dashpot. What do you mean by the term mass? You know that mass is a property of a body which stores kinetic energy. What does it mean? That because mass can store energy, and that energy is by virtue of velocity. So that energy is basically the kinetic energy. And the basic laws of forces, that if we apply a force on a body, then the body opposes that force, and that opposing force is basically proportional to the acceleration of body. These are the basically the mathematical model of this system. What do we mean by this term, that this is the mathematical model of that system? Consider any body, any mass. Consider a duster or a pencil box or any mass lying on a surface. That is a physical system. If we apply a force on that system, it will start moving. If we want to represent that physical system mathematically, so we can mathematically model that system, so we can analyze that system mathematically. So we want to represent that physical system by a mathematical equation. So this mathematical equation, which is known to us, F is equals to ma, that force which is applied on the mass, and the mass will oppose that force, and the opposing force is basically directly proportional to the acceleration of that body. So this mathematical equation is basically the mathematical model of this simple system of this, or of this mass. So here F is equals to ma represent this mathematical model of this physical system, and where F is known to us, F is basically the opposing force. Similarly, mass, M is the mass, and A is the acceleration. So whenever we have this type of physical system, whenever we involve a mass in our systems, we will represent that physical mass with the help of this mathematical equation. This is one of the basic element you can find, or you can see in the mechanical translational system. Similarly, when we move toward the spring, this is the basically the second major element which you can see, which will be available, which is available in the mechanical translational system. Spring is the element which stores potential energy. Basically, when you stretch this spring is expand, or whenever you compress this spring, this spring compress, potential energy is stored. Actually, spring is, we discussed, that mass is stored energy by virtue of motion. Similarly, we can say that the spring is stored energy by virtue of displacement. Whenever you compress, it displaces. Whenever you expand, it expands and it displaces. So displacement is the major cause of the energy. So this energy is potential energy. Mass, spring stored energy, in potential energy. If a force is applied on a spring, K is the stiffness constant or spring constant, then is opposed, then this is spring oppose that force, and opposing force is due to the elasticity or stiffness of the spring. This opposing force is proportional to the displacement. As you displace more, this four opposing forces will be more. This is this thing you can easily intuitively imagine. The thing that whenever you are compressing any spring, you will feel an opposing force from the mass. Similarly, whenever you try to expand that spring, mass or spring, you will face an opposing force from the spring. So this opposing force is directly proportional to the displacement. The greater the displacement, greater this opposing force will be. In this case, basically, the stiffness constant. So here we can say that this physical system, or the basic one of the basic major element of any mechanical translational system, can be mathematically written as can be mathematically represented as F is equals to kx. This is basically the mathematical representation of this physical system, where F is the opposing force due to the elasticity of a spring. Similarly, K is the stiffness or the spring constant, and X is the displacement. Third basic element which you can see in any translational system is damper. Damper is basically the friction, or we can say the dashboard. Basically, damper represent the friction of the system. If a force is applied on a dashboard, and this is basically the friction of any body. Whenever this mass will slide, it will face a friction, and this dashboard or this friction also is also one of the major part which you can visualize in any mass in mechanical translational system. And this mechanical system can be represented with the help of this mathematical equation, or the mathematical model of this physical system. Or friction is basically this modeled by this mathematical equation. What does it mean? F is basically the opposing force due to friction. Whenever the mass will start sliding, it will feel or face an opposing force due to friction. This is that force, and this is directly proportional to the velocity of that body. So B is the frictional coefficient which depend upon the surface or thing which is creating the friction. So F is the opposing force due to the friction of the dashboard, B is the frictional coefficient, V is the velocity. So these are the basic elements which you can see in any mechanical translational system. I hope that this term translational is clear to you, as this is one of the major type of the mechanical system. Second important, or the second type of mechanical system which we will study in this course, is mechanical rotational system. Mechanical rotational systems, it clearly denotes that this term is self-explanatory, because these are the types of system where the system moves about a fixed axis. These system mainly consist of three basic elements. Those are moment of inertia, torsional spring, and the dashboard. Basically, the major difference between the mechanical translational system and the rotational system is the path of rotation, or the movement or the motion. Basically, this mechanical system rotates, and that the translational system moves along a straight line. So here the major difference which is created in those system are there we apply a force. Here you can replace that thing with the help of torque. And similarly, displacement will be replaced by the angular displacement. Similarly, velocity will be replaced by the angular velocity, and the acceleration will be replaced by angular acceleration. So the basic element which you can see in any mechanical rotational system are moment of inertia, torsional spring, and the dashboard. Moment of inertia basically stored kinetic energy in any rotational system. So, if a torque is applied on a body having moment of inertia J, then it is opposed by an opposite torque, and that opposite torque is due to the moment of inertia, and this opposing torque is proportional to the angular acceleration. So, this torque or opposing torque due to the moment of inertia is directly proportional to the angular acceleration, and this J is basically the moment of inertia. Similarly, alpha is the angular acceleration, and when we talk about the torsional spring, this is the spring facing the rotational movement, and we say that in torsional spring, potential energy is stored, and similarly, the opposing torque produced by the elasticity of this torsional spring can be represented by the mathematical equation tau is equals to k theta, or you can say this opposing torque is the opposing torque produced by this torsional spring is directly related to the angular displacement. Here k is the stiffness constant of the spring. Similarly, T is the opposing torque, K is the torsional spring constant, theta is the angular displacement. Dashpot or damper in the rotational system is basically the friction which we model in the rotational system. So that friction will be shown or modeled physically by this damper or dashpot in rotational system, and here this opposing torque produced by this damper or friction is directly proportional to the angular velocity, and this b is the basically the rotational frictional coefficient. So these are the three basic elements which you can see in any rotational system. Let's move towards the electrical system. Electrical systems are mathematically in rotational system, force F is replaced by the torque T, hence displacement X is replaced by the angular displacement. As the rotation, as we didn't have any linear movement or movement in the straight path, we have rotational movement. This displacement is replaced by the theta, angular displacement, velocity is replaced by the angular velocity, and acceleration is replaced by angular acceleration. So in the last, we will study the electrical system. We have studied in various courses that major electrical systems are basically composed of three basic components: resistor, inductor, and the capacitor. These physical resistor, inductor, and capacitor can be mathematically modeled by their mathematical representation or mathematical equation, which is commonly known to us. For resistor, we represent that resistor with the help of this mathematical equation: V is equals to IR. For inductor, we represent that physical inductor with the help of this mathematical equation: VL is equals to LdI by dt. And for capacitor, we used to represent that capacitor with the help of this equation. What this equation means, that voltage across the capacitor will appear only if there is a current flow. So whenever there is a current flow, voltage will appear. Similarly, voltage across the inductor will appear whenever there will be a change in current. Di by dt may represent the change in current with respect to time. Similarly, current through the capacitor will only flow if there will be a change in voltage across the terminal of capacitor. So we we know the basic elements of all these types of system: mechanical, translational, rotational, and the electrical systems, and that physical elements can be represented by their equivalent mathematical models. So these type of system we will study uh, in our examples. So one important thing which you must know, that there are some energy storage element. So whenever we talk about the electrical system, capacitor, inductor can energy store energy in rotational and translational system. Mass can store energy. Similarly, moment of inertia can store energy, and the spring can store energy. And how they are related: capacitor store energy by virtue of voltage. So voltage is basically the physical variable, and the energy relation of capacitor is denoted by half CV square. Similarly, inductor store energy by virtue of current, and mass store energy by virtue of velocity. So and the moment of inertia by virtue of angular velocity, and spring by virtue of displacement, which we discussed it. uh, so these are the basic relation which you should know about these basic element which can store energy. We will use this relation in the next lectures. So these are the basic components in the system. Let's move toward a basic example, and we will discuss that how we can model a system, how we can form a different. You might have studied that how we can form a differential equation, but we will just have a review that how we can model a system in time domain. First, we will form a differential equation of that system, and finally, then we will move towards the time domain analysis.
Okay, let's start with a very basic mechanical translational system. This is example number 1, in which we have a mass which is lying on the surface, and we have applied a force on this mass. This mass will start moving, and this mass will also face a force of friction. Whenever we want to model any system in time domain, we want to represent this system with the help of differential equation. So before forming the differential equation, we usually mark this system with the nodes, and the general rule for marking that nodes are, we usually mark nodes at the point where we have a mass. So at this point I want to draw a free body diagram. For free body diagram, I am drawing this point as my node x of A. Here at this node XA, we have 3 different forces. One is applied force, second the force due to this mass, and third is basically the force due to the friction. The applied force is usually modeled like this. Similarly, we have a mass, and we used to represent mass with this, and friction is represented by a damper. So these are the 3 elements, and this is the basically reference point. This is my force applied, this is my mass, and this is damper. So start forming the differential equation. When we form the differential equation, we used to take help with the law of forces, that forces applied must a node must be equal to the reactive forces. So here the forces applied is basically this F, and the reactive forces are F of mass. Similarly, second is the force due to the friction, or you can write F this force. So this mass can be mathematically represented with the help of the mathematical equation, that is equals to F is equals to ma. So the mathematical model to represent this physical quantity is m into a. Similarly, the physical force of friction can be mathematically written with the help of mathematical equation, F is equals to BV. The important thing which we consider whenever we are forming the differential equation is that whenever we apply the force on this mass will start displacing. One may be interested in the displacement of this mass, and similarly there is another important parameter which is velocity. So one may be interested in the displacement, or any other designer or analyzer who is analyzing system, he or she may be interested in the velocity. So there are two important parameters here in the system. One is the displacement of this mass, similarly second is the velocity of the mass. It depends upon the designer that which parameter is basically important for him or her. So here we are considering velocity as our output or our important parameter. I want to visualize, or I want to see how the velocity changes of this mass after the application of this input at different instants of the time. So I want to visualize the response where output is velocity. So I will try to transform this whole equation in terms of velocity. This is already in the velocity. I can easily transform this acceleration in terms of velocity. So I can write here this mass into acceleration can be written as dv over dt plus bv. This is the basically applied force. So I will try to rearrange this equation or simplify this equation. So my differential equation dv over dt is equals to f by m minus b over m into b. This is my differential equation. I will say this is equation number or equation A. So this differential equation represents the basic mechanical translational system, that how this velocity changes with respect to the time. This is basically the differential equation. We used to solve these differential equation in our mathematical courses, and we have a complementary and particular solution for these differential equation, which basically represent the responses of this differential equation. Here we will not use those solutions to find the solution of this differential equation. We will use the tool MATLAB to represent this system or to represent this differential equation, and with the help of the MATLAB we will evaluate the response, and we will try to visualize that how this response of this system changes with respect to time, or how the velocity of this system changes with respect to time, and how you can see that how this differential equation represent this physical system. So start moving towards MATLAB. This is the MATLAB environment. Here you have different windows. You have a current folder window which can be changed from here. If you want to change your current folder, you can navigate from this point and you can select any folder where you want to be. So I have a current folder. Similarly, there we have a command window in which you can write code, and you can execute every line instantly. And we have a editor window. Similarly, we have a workspace window. Workspace window is basically a window where variables which you define in your code you are available. This is the editor window where we used to type our whole script. So how we can represent this mechanical system here in the MATLAB? We can do it easily. First of all, that we want to represent this differential equation. We know that this sign represents that this is a comment. Wherever we have this percentage sign, we will this percentage sign represent that this line of code will not get executed. This is just for the reference or for your understanding. So how we can represent this system? We can represent easily by defining a function of the differential equation. What do we mean by the term function? I hope that you have already used this MATLAB software. We have different functions here. If you want to find the determinant of any matrices, you can use the syntax or function det determinant. Similarly, for inverse, we have a different function. Similarly, for multiplication, and there are several different functions. So whenever we have a function, we can also make our own functions here. So for defining a function, you must write a function at the starting. So this MATLAB might understand that you are going to define a function here. I am going to define a function of a differential equation of dv by dt. Here we didn't use any backslash, you can write it directly as the dv dt. So secondly, what is the name of this this function? So here you can write any name. We have written cruise underscore speed. You can write this as dv dt is equals to mass underscore spring. So you can write any name, you can select any name here. So here for mass spring only, you can use this as a mass damper. We didn't have any spring here, we have only mass and a damper here. So you can name it anything, whatever you want. These are the two important variables which you should consider here. One is the time of observation, second is the velocity. For how much time you want to observe this system response. Second is the velocity. If you take 200 seconds, then you can view the response for 200 seconds. So these are the two important parameters for us. These are the elements values: mass, damper, and the applied force. Whenever anyone is analyzing or designing any system, he or she must know that what will be the value of mass, similarly how much force is applied, similarly what is the damping coefficient depending upon the surface of that of this area. So here we have any value mentioned. You can change these values as per your choice. Our mass is basically 750 kilograms. Similarly, 30 Newton second per meter is the friction coefficient. Similarly, we have applied a 300 Newton force. One important thing, one which you should consider here, this force is basically a step force. A step force means that a 300 Newton force is applied, which is basically of a form step. What does I mean by this comment? This means that we have a 300 Newton force which is applied at this time t equals to 0, and this value is 300 Newton. Okay, and this is step force. So here these are the element value. This differential equation which we want to represent is dv by dt fa over m minus b over m into v. This dv, so we write it here as dv dt. No need to use this backslash here. For differential equation we will use backslash here in fa over m minus b over m into v. This is the basically our system differential equation. So we have defined our system here. One important thing before executing or before moving forward is that whenever you named any function, this script must be same with the same name, must be saved with the same name. Here this you have changed the name of the function mass damper, but the script name is different. So first of all we have to change this. I named it as the same name which I use to define function. So this is basically mass underscore damper. What happened whenever you call this function anywhere in any other script or on command window? This mass damper, first of all, this MATLAB will reach this M file. After reaching that, then this function can be retrieved. Similarly, we have example number 1 here. This is the basically initial velocity. What does it mean? Initial velocity means when you applied a force on this mass will start moving. Before the application of the force, at that time instant when the force is applied, this mass is at rest. No velocity is present in this mass. This is basically the meaning of initial velocity. At that time when the force is applied, this mass is at rest, no movements, and similarly no velocities. You can change this value. If you change this value, it means that at that instant when the force is applied, there must be some initial speed or the initial velocity, whatever value you put here. So this is basically the differential equation solver. The thing which we want to escape is the basically differential equation solution, which you have performed in the different mathematics course. So here we will use MATLAB. MATLAB will use ordinary differential equation solver 45, which will solve this function of the differential equation, which is now named as mass underscore damper. So this mass underscore damper. So MATLAB will call this function, which is solved by this solver, and the time of observation is basically starting from 0 to 200 seconds, and the initial velocity is v0, which is 0. The solution of this system will be stored here in this vector t comma v. We carry the time information, we will carry the velocity information. Plot t comma v means this system response will be plotted with the help of these variable. T is time, v is velocity, grade on basically mathematical grids will be available on the plot. Title, this title will be available on the figure. So I will execute this code and we will see that how the system respond after the application force. So this is the basically we can execute it from here. Run, and we will have a figure here. So this is the basic response. You have observed the response for 200 seconds, and this is basically the speed of this mass. Whenever you applied a force, initially the velocity is 0. That means that we have taken the initial velocity 0, and after the application of this force, this mass start moving, and finally it take a constant velocity, and it will move on this constant velocity till the force is present. So this is basically the physical interpretation, or you can imagine the response of this system, that after the application of force, this mass will start moving. Initially the velocity changes, and finally there comes a time when the velocity gets constant as force is constant. So this mass will start moving and remain in this velocity up till we have a force here. So this differential equation basically characterize this complete mechanical system and can represent that how the dynamics or how the velocity and the displacement changes with the application of force. So this is basically the objective of our time domain modeling. We want we want our mechanical or electrical system to represent with the help of these differential equation, and these differential equation represent or means that how the system respond to any input. This is the basically example number 1, in which you studied that how we can represent a system with the help of differential equation and what does this differential equation mean. I hope that this topic is clear to